Hi friends, just wanted to finish up our lesson on section 2.7 inverse functions because we really didn't get the opportunity to really finish that in class. So quick review here. So these are the steps for finding an inverse. Number 1, replace f of x with y if it's not already there. Step 2, transpose the x and the y. That really truly means just flip the x and the y, switch places. Step 3, solve for y, of course, using inverse operations. And then step 4, replace y with inverse notation, f inverse of x. Remember, that doesn't mean reciprocal. That is inverse notation. And then, of course, verify. F of f inverse is going to equal x, and f inverse of f of x will also equal x. So let's start off with actually going through these steps and finding the inverse, and then we'll graph both. So first step, replace f of x with y. Y equals 1/3 x cubed minus 3. Switch the x and the y. X equals 1/3 of y cubed, minus 3. All right, add the 3 over. X plus 3 equals 1/3 y cubed. Multiply both sides by 3. 3x plus 9, cancel, cancel, equals y cubed. And then undo that cube by taking the cube root. Now, as I'm writing the inverse here, remember this is a cube root function, and a cube root function does not have a domain restriction. So we are in the clear. The function is a one-to-one function, and its inverse is also going to be a one-to-one function. Both of them have no domain restrictions. So look at your function, think about what it should look like. So first of all, there's no there's no horizontal movement here. There's no parentheses. So we got no horizontal movement, so we're staying right on the y-axis, and we have a vertical shift down 3. So 0, -3. There we go. And that 1/3 in the middle, remember, is going to just squish that function right at its center, right at x equals 0. So let's plug in a couple of numbers here. Let's plug in the 1. So f of 1, 1 cubed is 1. 1/3 of 1 is 1/3. 1/3 minus 3 is -2 and 2/3. So over 1 down 2 and 2/3. So you see what's happening. It's zhushing it, flattening it right in the middle of the function at x equals 0. The next easiest thing to fill in is going to be x equals 3. 3 cubed is 27. 1/3 of 27 is 9. 9 minus 3 is 6. So f of 3 is 6. So there we go. So think about how the fact that we've got a truly odd function here. So if we have a point here, there will also be one here. And if we plug in a -3, -3 cubed is -27. 1/3 of -27 is -9. And -9 minus 3 would be -12. So we'll be zoop right down there. So here is the given function. Now, here's what we can do. The easiest way to graph the inverse of this function would be to, just what we said in our steps, to transpose the x's and y's. So let's do this in a different color so it looks super cool, because that's what we like. Now, let's think about this. If we have a point at 0, -3, we are going to have a point at -3, 0. We're going to have one right there, which makes sense. What is f inverse of -3? Well, 3 times -3 is -9, and -9 plus 9 is 0, and the cube root of 0 is 0. That's why we have a point there. All right, let's also transpose this. This is 3, 6. So if there's a point at 3, 6, there's going to be one at 6, 3. Let's put in a 6. So 3 times 6 is 18. 18 plus 9 is 27, and the cube root of 27 is 3. So f inverse of 6 is 3. Hooray! So I think we've proven that now. We're not going to go crazy with the fractions. We're just gonna take the inverse function at its word, which is its definition. So here goes. This is over 1 down 2 2/3. So let's go down 2 2/3, and then let's go over, did I say that right? I better write it down. So over 1 down 2 2/3. So we're going to go, there we go, back 2 2/3, and then up 1. Ooh, I was about to get it wrong. So if there's 1 there, there's also going to be 1 there. And this point right down here is at -3, -12. So if we go back 12 and then down 3, we're going to have a point here. So here is our inverse function. There's our inverse function. And if we draw the line y equals x through here, even though I did draw it freehanded, it's still in pretty good shape. This yellow line should be its axis of symmetry for both the given function and its inverse. That's a nice looking little problem. All right, let's take a look at this one. This is one like you're going to see in your homework where you're just given this complete wackadoo function. And we want to find its inverse graphically. So the first thing I'm going to do is I'm going to list 1, 2, 3, 4, 5, 6, all 6 of these points. So here's the function. So, all right, where are we starting? We are at -7, -6. Then we are at -6, -2. This is -3, 0. This is -2, 3. This is 0, 4, and 2, 8. So our inverse function is just going to be all of these transposed. -6, -7, -2, -6, 3, or 0, -3, 3, -2, 4, 0, and 8, 2. So if we plot these points, we should see the inverse. Back 6, down 7. Back 2, down 6. Back 2, down 6. 0, -3. 3, -2. 4, 0. And 8, 2. So now, using my handy dandy note card as my straight edge, there we go. There's our inverse. So once again, if we plot the line y equals x through here, that becomes the axis of symmetry for the two inverse functions. All right, so one more problem to do, and probably the best thing we can do is look at this one on the graphing calculator in terms of its graph here. There we go. Clearing everything out. So when we put this in our graphing calculator, let's take a look at it. Now, first of all, thinking back to our previous section, this has a domain restriction. This has a domain restriction, and if we set 3x minus 1 equal to 0, 3x equals 1, x equals 1/3, we have a vertical asymptote at 1/3. 1/3 is omitted from this function's domain. So I'm going to bring up my fraction windows. So x plus 2 on the top, 3x minus 1 on the bottom. Take a look at this little graph. There's that vertical asymptote at 1/3, and probably have a better view if you hit zoom 4. And we want to see, we want to find out what is the inverse of this function. So let's move that out of the way and let's go through the steps. So there we go. There's our domain right there. We're just letting it, or our vertical asymptote, let it hang out on the side. So we're going to go through the steps. So step 1, replace f of x with y. Y equals x plus 2 over 3x minus 1. Next step, swap the x's and the y. Even though there's 2 of them, we're still going to follow the steps. So x equals y plus 2 over 3y minus 1. And now our job is to solve for this y. So this is why we reviewed solving literal equations in the summer work and also back in the P chapter. Because we need to do it right now. We need to isolate the y. So how are we going to do that? Well, the first thing I'm going to do, I'm going to put x over 1 and realize that I have a fraction set equal to a fraction. And then from there, I am going to cross multiply. I cross multiply over an equal sign and only over an equal sign. So we end up with, and I'm moving over here to the left, x times 3y minus 1 equals 1 times y plus 2. So 3xy minus x equals y plus 2. Now consider this. And if we want to isolate the y, then every term that has a y in it needs to all come to one side. And if it does not have a y, then it needs to go the other side. So we're going to flip the negative x, and we are going to flip the y. So we end up with 3xy minus y equals 2 plus x. Next, what is the y relative to the left-hand side? The y relative to the left-hand side is the greatest common factor. It's the GCF. So we're going to bring it out. We're going to factor out the GCF y and get 3x minus 1. Now, to get the y by itself, we simply need to divide by 3x minus 1. And that is our inverse. Last step, of course, is to use inverse notation. So f inverse of x equals 2 plus x over 3x minus 1. Now, what you need to do now is compare the given function to the inverse function. What? Well, if we go back to our graph, and let's take a look at it here, what I see is that if I run the line y equals x right through the middle of this graph, it is its own inverse. The left hand or the right hand side is exactly like the left hand, the right hand. If we could fold the graph on the line y equals x, the left-hand side would lay directly on top of the right-hand side. It is its own inverse. Now, the other thing I wanted to show you here was the verify part. So, if we've got f of x equals x plus 2 over 3x minus 1, and f inverse of x equals 2 plus x over 3x minus 1. And of course, 2 plus x is exactly the same thing as x plus 2 by the commutative property of addition. So look at what happens if I compose the inverse function within the given function. So f of f inverse. So f of 2 plus x over 3x minus 1. All right, which means that we are going to be inputting here and there. All of that is going in, both of those spots. So 2 plus x over 3x minus 1 plus 2 over 3 times 2 plus x over 3x minus 1 minus 1. And this is why we learned about rational expressions back in the P chapter in chapter 1. Because now we need a common denominator and we need to combine like terms. So here goes. So my common denominator, of course, is 3x minus 1. So I am going to multiply everything by 3x minus 1 over 3x minus 1. Remember, it's a quantity. So 2 plus x over 3x minus 1 times 3x minus 1, they cancel, and I get 2 plus x plus 2 times 3x minus 1. There we go. Goodbye fraction. To the bottom, the quantity, 3x minus 1. First, I think, well, no, never mind. 3x minus 1 times 3 times 2 plus x. Remember, the 3 right up there is only going to that numerator. So the 3x minus 1 will cancel with the 3x minus 1 and leave 3 times 2 plus x minus the 3x minus 1 times the negative 1. Negative 1 times 3x minus 1. There we go. So this is what we end up having to simplify. So let's do it. Here goes. So 2 plus x plus 6x minus 2 all over 6 plus 3x minus 3x plus 1. So we end up the 2's canceling, the 3x's canceling. We end up with 7x over 7, which of course is x. And that verifies. Remember, this is the algebraic verification. We saw the graphic verification, and that's where you see the x, the y equals x as the line of symmetry. This is the algebraic verification. So there you go. There is a quick review of finding inverses.